Last time we talked about all the three major goals, and we classified the attacks based on each goal attacks. So during categorization of the, inshallah, we gone. طيب بسم الله الرحمن الرحيم. Okay. So we started to talk about security and cryptography, and we talked about the security services and the mechanisms. So what happens is that ITU-T, which is the standardization organization, they produce like some documents related to security, and in these documents they define the major security services that need to be in place in any system. And these services include data confidentiality, of course, which is hiding the information. We need to have integrity. We need to have authentication. Authentication means that each user needs to provide some identity or some proof that he or she has sent or accessed the system. Non-repudiation, which means that we need to provide some proof that you sent, that this proof is unmodifiable, which means that we cannot later on say, I did not send this information. Okay, so that's what we mean by non-repudiation. Access control means that we need to have different levels of access to the system, different privileges. So if you provide credentials for a user level access, you cannot, like for example, set up a new program on a server, or you cannot modify the content of some files on the system. So the different levels of access are controlled by what we call access control. So based on these services, they also described what we call security mechanisms. Security mechanisms are the actual algorithms that we need to use to provide these services. Okay? And they provide the mapping. So this mapping describes the fact that if we want to have confidentiality as a service, then we need to probably use encipherment and or routing protocol as a mechanism. So what we mean by a mechanism is that encipherment is a way to provide information concealment or hiding the information, which provides confidentiality. Data integrity data integrity refers to some mechanism by which we can actually, when we send a packet, we append to this packet some like hash of this information. So if you change this data in any way, the hash will become invalid. Okay? So the receiver can recognize that the integrity of this packet has been affected. So it rejects the whole packet. Similar to a checksum, as we said, but this is much more complicated. So if there is any modification to the content of the message, the hash will become invalid, in which case we can say that this message is rejected. So that's what we use to guarantee the integrity. We have also what we call digital signature. So not only do we actually use a hash like this, but we can stamp this hash with your signature, so that not only do we guarantee the integrity of the message, but we can say that this is for sure coming from you and not from anybody else. It's similar to when you have a document in the bank and you sign it. So this signature is only done by you, so we know that this is coming from you, and this guarantees what? This guarantees data integrity, and it guarantees also non-repudiation. Okay, so you cannot deny that you have signed this document. Authentication, we talked about authentication, that authentication can be done using different mechanisms, using user ID and password. This is the simplest way of authentication that we know of. But there are multiple ways. You can use a key to authenticate yourself to the system. You can use biometrics. You can use iris. You can use fingerprint. You can use EEG signal. You can use many things that are unique by you, that we know that you are the one who logged onto the system, or you are the one who accessed this information and nobody else. So that's the authentication. By this authentication as well, we can provide certain access control. So using your user ID and password, you have admin access to a certain server. So you have very high privilege. Or using this user ID and password, you have low privileges, which means that you have limited access to the system. Type traffic padding. We know padding, صح? We discussed padding in network 1. We use padding for what? حد فاكر؟
Filling the medium.
Filling the medium. No, actually, what we did is that we know that, for example, the IP packet has to be 32-bit word aligned, صح? So there is a variable part in the IP packet, which is what we call options, فاكرين? So this options is variable size. So if this option is not aligned with the 32-bit word, مثلا there is like 5 bits or something, so we use pad to add some dummy bits to align the packet with the 32-bit word. Okay? So that's the padding in general. Padding in general is adding some dummy bits to the message with a specific objective. Here the objective is to align the packet size with the 32-bit word. In security, we actually use padding for a totally different thing. In security, what we do is that if the packet size of the IP packet or the frame size is fixed, okay, this will make it easier for the attacker to use that fixed size to try to do some traffic analysis and break the communication. So if you know that the message has fixed size, okay, so that simplifies the job for you, right? So if I want to confuse you more, add variable dummy bits. So we here in security, traffic padding, not with the purpose of having fixed size or aligning, no, we actually want to confuse you more, confuse the attacker more by adding different size of dummy bits. So the only one who can recognize the size is the one who has the key, because this padding is also encrypted with the message. So only the one who has the key can decrypt and then can read the size of this pad, and you can extract it and get the message. But the attacker, when you see something encrypted and with variable size, this makes your job much, much harder. واضح كده ولا واضحة كده؟ Okay? So that's traffic padding. Routing control is about changing the route of the packet every time. Because if you know that so if you have a source and a destination, and you have a specific route that the packet goes through every time, this makes tapping also easier. But if I tell you that, okay, so one time I use this route, one time I use this route, one time I use this route, one time I use this. So every time you listen to a route or you listen to a link, I will change the link. Of course, that might imply that we don't always select the best path in that case, but we can slightly degrade the performance by selecting suboptimal or best path to confuse the attacker by changing the route every time. واضح كده؟ طيب notarization بقى. Notarization ايه notarization؟ حد يعرف notary public? Do you know what notary public is? So if I want to send a message to, for example, to the Ministry of External Affairs of the US or I want to buy a house or something like this, or I want to send a message to abroad. So if it goes to the government of any country, and this government would look at the document, they need to know that this document is coming from you. So if you send it remotely, they have no guarantee that this is actually coming from you and it's authentic. So what we normally do, if you want to send a document to the US, for example, what you do is that you go to the US Embassy here. So the US Embassy acts as a third-party notarization entity which notarizes and vets your document that this document is really coming from Amr and it's an original document. How do they do this? By looking at your ID, they look at the document. Yes, this document is coming from you. It has the stamp and everything. And then they stamp the document and say, yes, this is coming from Amr, and yes, this is original. Then you can take this document later on and send it to the US. The US will be more confident that this is really coming from you and it's an original document. So notarization is about having a third party that guarantees that this communication is really original and the source is actually sending this message. So the source, I cannot later on say, no, I did not send this message to the US. No, you did. And there is a third party or the embassy that can prove that because they have a copy of this message as well. فهمنا كده? So notarization is about having a third party that monitors the communication to make sure that the sender is the one who's sending, the receiver is the one who's receiving, and the communication is going normal. So this could be a certificate authority or a third party of some sort that looks at the communication and say, yes, this is going on fine. ماشي? So that's notarization. So this table here maps the services with these mechanisms. So if I want to have a certain service, I might need to combine one or more of these mechanisms to provide that service. So hiding the information or confidentiality can be provided by either encryption or routing control or padding or a combination of them. ماشي? So I can use a combination of certain mechanisms to provide that. Data integrity can be provided by ensuring the integrity and also by ciphering the signature using the key. That's also another way of ensuring data integrity. Or by having a signature, that's also another way of ensuring integrity, and so on. And non-repudiation and so on. So these are the services and the mapping between these services. And see, cryptography here is used here. So it's used in many services, so mechanisms. So of course, the theoretical explanation of these mechanisms refers to the fact that the implementation of these mechanisms is very sophisticated. And it's not as easy as we describe it now, but it's very sophisticated. So talking about or covering these mechanisms in this short part is actually almost impossible. So we will talk about one aspect of this, which is what we call a cryptography. Cryptography or encryption is the process of ciphering the plain text into what we call a cipher text. And this way, the attacker or the eavesdropper cannot get any information from this message. So cryptography is the most important aspect of security. And it's as you cryptography can be classified into two categories: either symmetric key encipherment or asymmetric key encipherment. By the way, encipherment, encryption, cryptography, all of them refer to the same thing. Okay? طيب. Symmetric key talks about the fact that from the name, we use the same key, we use the same shared key between the source and a destination. And this key is used to lock the message in a box that nobody else can unlock this box except the destination. So the key is only shared between the source and the destination. So in other words, so the source, what the source does for the case of symmetric key is that it uses encryption algorithm using the key, and it applies that to a plain text to produce what we call the ciphertext. Okay, kida? So the ciphertext will be sent to the destination. What the destination will do in that case, it will apply a decryption algorithm using the same key, okay, to the ciphertext to produce the plain text.
How would the receiver know the key if I send the information for the first time?
Yes, so that's a very good question. So how do they share the key? We assume that this key is pre-shared through some secure communication, and it's out of the scope. In fact, sometimes they use asymmetric encryption to exchange the key, which is symmetric. Okay? But our assumption is this shared key is exchanged somehow. Okay? Only the source and the destination, they know about this key. So for asymmetric key encipherment, the difference here is that we apply a different key, we call it key public. Okay? Using the encryption algorithm to the plain text to get the ciphertext. Then we send the ciphertext. Then the destination will use decryption using key private to the ciphertext to gain the plain text. And so in other words, we're using different keys on either side. Okay? But of course, there is a relationship between these keys in such a way that it makes the decryption is the reverse operation of encryption. So these keys have to be designed carefully so that the decryption will be the mirror of encryption. The implication of this is very interesting. So remember that the symmetric key, the shared key is per communication between each two entities. So if you want to communicate with n different nodes, how many keys do you need to have? N different keys. Okay? If n different nodes wants to communicate with you using asymmetric key, how many keys do you need?
One.
Two طبعا لو ما يعني البابليك key والprivate key. بس you're right. Yes, it's only one. طيب بمعنى يعني اني if you have n nodes in the network, okay, for symmetric key, how many keys do you need? Assuming that all the nodes want to communicate with each other. Okay? For each pair, you need one key. For each pair of communication, you need one key. So that there is no repetition here. So what is this in math? مش factorial بقى. أيوة. Combination, because there is no repetition. We don't need to have repetition here. So it's NC2. So we need NC2 of keys, which is n times n minus 1 over 2, which is O of A, O of n squared. ماشي? What about the case of asymmetric? For the case of asymmetric, anyone needs to send you a message, he needs to use your public key. So the keys are not attached to the communication. The keys are attached to the user or to the node. So anyone wants to send you a message, he should use your public key. Okay? And then in order for you to decrypt this message, use your private key. So in other words, in asymmetric key encipherment, the public key is known by everyone. It's not a secret. Unlike shared key. Shared key, the key has to be a secret between source and the destination. For asymmetric key, the public key is public. Everybody knows it. But the private key is only known by you. واضح كده ولا لا؟ Okay? So this way, for n nodes, how many keys do we need to have?
in public
No, n times 2, يعني for each node we need 2 keys, right? So 2n, which means O of A, of O of n. So that's one of the disadvantages of symmetric encryption. In terms of key management, we need يعني number of keys which is high. It turns out asymmetric encryption is much more complicated. It requires computational requirements يعني, which is very high. So that's why typically we still need to use symmetric encryption, even though we need many keys in the network. And in fact, in many cases, they use the public or the asymmetric encryption to just exchange the keys, and then from then on, we can use symmetric encryption for encrypting the communication. So that's what typically happens. Why do we not use the asymmetric encipherment for encrypting the actual traffic? Is because it's very highly complicated. So we use it once. الإجابات اللي سؤالك يا إيهاب. We use it once at the beginning to just exchange the symmetric key. Once we exchange the symmetric key, we use the shared key to encrypt the traffic. ماشي كده؟ يعني again, this is details. يعني you don't have to know all these details. يعني. So طبعا there's no way we can cover all these techniques, and we will cover only symmetric encryption. So symmetric encryption is all about applying encryption algorithm. The encryption algorithm, by the way, is it secret?
No.
It's public. Everybody knows the encryption algorithm itself. Okay? So it's standard. Like you have DES, you have triple DES, you have AES. All these are public. Everybody knows them. But what's missing? What's the secret here? The key. The key is the only thing that's missing. Okay? So the key, we apply the encryption algorithm using that key. Even the size of the key is known, by the way, in many cases, because it's part of the standard. We apply this algorithm using the key, and we get the ciphertext. We can send the ciphertext. The ciphertext is exposed. Anyone can listen to it. You can have like some, I don't know, like packet tracer or Wireshark or something like this, and you can sniff the packet and get the ciphertext. It's exposed. But can you get anything out of it? Only if you know the key. So you send this ciphertext on the secure channel, and then you can apply the decryption on the other side. But the condition here is that you need to have the key. If you use the same key to decrypt, again, the decryption algorithm, similar to the encryption algorithm, is public, is well known. If you apply this decryption algorithm with the same key, then you get the plain text. So any symmetric key encryption has to satisfy this condition, is that if you apply the encryption, then decryption, or decryption using and then encryption, so the order doesn't matter. As long as you're using the same key, okay, then you will eventually reach to the plain text. ماشي؟ واضحة دي؟ So that's the condition that any symmetric key encipherment has to satisfy. So based on that, if Alice encrypts the plain text and get the ciphertext, Bob will get the ciphertext. If Bob decrypts the ciphertext using the decryption algorithm, he gets P1. Is P1 equal to P? Well, if C is E of K to the plain text, this looks like this. صح? So based on that condition, he will get P1, which is actually P. So that's يعني, this is like a simple proof that actually this is reversible, and Bob, he will be able to recover the plain text from the ciphertext, assuming that he uses the same key. Okay? طيب. The good news is that we can secure the communication using P, but the bad news is that there is an attacker sitting on the other side, tries to use all sorts of intelligence to break this communication. So he can use the traffic analysis, or what we call crypto analysis, to try to break into the communication. So crypto analysis attacks are categorized in these 4 categories. So either the attacker knows only the ciphertext. That's the minimum. As we said, ciphertext is always exposed. So we can read it using Wireshark, using Packet Tracer, using any tool. Whether wireless or wired, you can read it. So the assumption that the ciphertext is hidden and the attacker cannot get to it, that's naive. That's not true. So the attacker at least has access to all the ciphertexts. Okay, so that's 1. 2, the attacker may not only have access to the ciphertext, but he or she can have access to a plain text that corresponds to one ciphertext. ازاي? How? Well, based on my knowledge about certain protocol, for example, HTTP, I know that at the beginning of the communication, the client has to send to the server a message with a specific text. Okay? Okay, so that's that. I'm assuming that in the beginning of the communication, the client has to send this message based on my knowledge about the protocol. So I will capture the ciphertext, and then I know the plain text. Okay? Then I get this pair, and then I can use that for attack. Okay? So that's...
If you know the text and you know the ciphertext, you can get the key?
It depends on the encryption. I will talk about that. Encryption. It depends on the encryption algorithm. It's not always true. It depends on the encryption algorithm. طيب, chosen plain text. ايه الفرق بين known plain text and chosen plain text? Chosen plain text, but the difference is that the assumption here is that the attacker has already control over Alice. And he can give Alice, he can fool Alice and give her any plain text. And Alice will be naive enough to convert it to a ciphertext. So it's not by any plain text based on a protocol. That I have control what plain text I can give you. Okay? So that's the difference. Here, it's based on chosen ciphertext. So I don't have control over Alice, I have control over Bob. So I can give Bob, I can give you this ciphertext, and Bob, as naive as he is, he will get it, and then he will give me the plain text that corresponds to it. So if you have this control, that simplifies the crypto analysis. So how? So using ciphertext only, in many cases, what you could do is that when you get the ciphertext, you can use a brute force based on your knowledge about the encryption algorithm, so you know that, right? And in many cases, as I said, you know the size of the key. So if the size of the key is 64 bits, how many combinations do you have? 2 to the power 64. So using brute force techniques, you try all the 2 to the power 64 on the ciphertext. You know the decryption algorithm, okay? Type. What is the ground truth here? The ground truth in many cases is to have certain assumption that they are communicating some English text. So if I get like some text that looks readable, okay, then most probably that's the right key. So I try all the different combinations, and then whenever I see a text that looks readable, then I say, oh, okay, so there is a high possibility that this is the right key. Okay, so I will use this key more and see if I can have more readable text, and I will apply this key again and get more and more readable text until I get some level of confidence, and then I stop. Okay, so that's using the ciphertext. If I know the plain text, which is number 2 here, if I know the plain text, depending on whether the encryption algorithm, if assuming encryption algorithm, I give you the simplest example. If the encryption algorithm is simply ciphertext equals to XOR the key with the plain text. طبعا in practice it's not as naive as this, but let's just assume. If you know one plain text that corresponds to one ciphertext, what's key? What's K? Yeah, so K equals to P1 XORed with C1. So if you know this pair, only one pair, you can get the key and that's it. Okay? But of course, in practice, the encryption algorithm is designed so that this process is not valid, and you need more intelligence more than just that to recover the key. ماشي كده؟ طيب. Syntax بقى assumes, as I said, assumes that the attacker has control. يعني there is a prior impersonation attack or man-in-the-middle attack that happened, which allowed Eve to have control over Alice. So I can give Alice any plain text, and then I can read the ciphertext that corresponds to it. So if that's the case, then I can say, okay, let me give her like a trivial text. I give her A, just A, and let's see what she produces. She produces O. Okay, so A corresponds to O. So let me give her B. Okay. So B provided a B. Oh, okay. So it looks like the encryption is just a shift register. It's just a simple shift. So A becomes O, B becomes P, and so on. So okay. So it looks like the key is like 15 or something like this. So let me. So you can, by controlling what plain text you give her, you can speed up the process significantly, right? The same thing can happen on this side, because instead of having control over Alice, you have control over Bob, in which case you give Bob the ciphertext. Again, you can give him a letter, and then you can get the plain text that corresponds to that. ماشي كده؟ So by knowing the chosen plain text or chosen ciphertext, the crypto analysis becomes easier and easier. So knowing only the ciphertext would make it very hard. Knowing known plain text, it makes it a little bit easier. Chosen plain text means that you can give her any plain text and get the ciphertext, in which case you can speed up the process significantly. واضح كده؟ So how crypto analysis works. So based on that, they classify the ciphers into two major categories. One is called substitution ciphers. Substitution ciphers, they map each letter in the plain text to another letter in the ciphertext, to another letter or group of letters. So assuming that we have the word hello, so the H becomes O, the E becomes P, for example. The L becomes K, and the other L becomes K, and the other O becomes L, whatever. So the hello becomes like this. So mapping each letter to another letter in the ciphertext. So that's what we mean by substitution ciphers. ماشي? Or transposition ciphers. Transposition ciphers, you don't actually map a letter to a letter, but you change the location. So this is transposition. You rearrange the letters, يعني you scramble the location of the letters, but you don't change the letter itself. طبعا changing the letter from here to here requires some kind of a lookup table. Okay? Transposition, if you have the word hello, and you have a key of 3, 5, 2, 1, 4, مثلا. This is the key. This means that the first letter will be number 3, so it's L. The second letter is number 5, so it's O. The third letter is number 2, which is E. And so on. So you're not mapping a letter to a letter, but you are changing the location. ماشي كده؟ Substitution ciphers are subdivided into monoalphabetic or polyalphabetic. Monoalphabetic is what we have described here. So we map a letter to another letter depending on its value only. Depending on the value of this letter only. يعني So L becomes K. So always L becomes K. Always. So it's one-to-one relationship. ماشي? From one letter to one letter. Always one-to-one relationship. That's why we call it monoalphabetic. Polyalphabetic بقى, the letter can be mapped depending on its value and some other factor. Could be its position. In other words, the polyalphabetic is actually a mix between the two. So the polyalphabetic assumes one-to-many relationship. So hello becomes a OP and then KNL. Okay? So the first L has been mapped to K. The second L has been mapped to something else. Why? Because the second L does not exist in the same position of the first L. So we map the first L to K, but the second L depends on its value and its position. واضح كده? So that's one-to-many relationship. So the letter can be mapped to any other letter depending on its value and position. So if this letter exists in the beginning of the word, it's different from the middle of the word, it's different from the end of the word. ماشي? So these are the two types. So based on this encryption algorithm, is it monoalphabetic or polyalphabetic? Most probably mono, because LL becomes OO, right? So that's mapping the letter irrespective of its location. Okay? Whereas for this one, of course, so for this one, it's most probably polyalphabetic because the LL becomes NZ. Okay? So in that case, it's most probably polyalphabetic. So the one-to-one relationship is not there. Otherwise, the L would be mapped to the same letter. So based on that, we'll talk about very simple two examples, and that's it. So the one example is what we call the additive cipher, or sometimes we call it shift cipher or Caesar cipher. Caesar because it's referred to King Caesar, who actually used to use that in the past, في العصور الوسطى يعني, to communicate with his officers in the battlefield. So this additive cipher is based on the basic letter table. So we assume that the plain text is small letter from A all the way to Z, 26 letters, okay? And the plain text can be any one of these, okay? So if we need to map the plain text small case and uppercase, then we have to add here. If we need to add special characters, then we need to add. So it becomes more than 26 here. It becomes Z مثلا 52 or Z 60 or something like this. The simplest case is that we want to map the 26 letters small case into any ciphertext. So the only thing we need here is a key, and the key here is just a number. Okay? So each letter will take a number from 0 all the way to 25, which is in total 26. And we have a key, which is a number, which is also between 0 and 25. So all we need to do is, طبعا لو 0 يبقى مفيش encryption. But if 1 to 25. So if 1 معناها ايه؟ 0 becomes 1, 1 becomes 2, 2 becomes 3, and so on. So instead of A, it becomes B. And instead of B, it becomes C, and so on. If K is equal to 2, معناها each letter is shifted by 2. 3 shifted by 3, and so on. Very easy. So the missing part is just a number, K, which is 1, 2, 3, all the way to 25. So based on that, the additive cipher becomes like this. We add we add to the plain text, we add k, which is a number. It's like we shift the letter based on this lookup table, and then we say mod 26 because we want to circle, we want to have like a circular shift. ماشي? So the decryption is simply subtracting. So if we have, like the plain text is 15, and the k is 15, so 15 plus 15 is 30. What is the value here? 30 mod 26, which is 4. Okay? So if we have the cipher text, assuming that the cipher text is A is 0, and you have k is equal to 15. So 0 minus 15, what is minus 15 mod 26?
0.
No?
Minus 15.
No?
Minus 7. 14.
Minus 15.
No?
And minus 15, what is 26?
Yes?
0.
No?
Minus 26.
Modulus 26 must be from 0 to 25.
26 minus 15.
This is the fundamental of modulo arithmetic.
26.
Hmm?
26. Is it 11? 11? 7?
Yes, it's 11.
Give me number.
26 minus 15.
Yes, so you cannot have a modulus of negative modulus 26. So you have to make that negative positive.
Convert it to 2's complement?
لا. So you have to add 26. Okay? When you add 26 to the minus 15, it becomes 11. What's 11 modulus 26? 11. So this is 11. بلاش يفتكر الكلمة دي ها عشان ما نجيش بقى في امتحان ودي أصل يعني
I didn't understand it. I'm sorry.
minus 15 modulus 26. This is exactly similar. If this number is more than 26, what do you do? You subtract 26, صح? صح? طيب, if this is less than 0, you have to make it positive by adding 26. ماشي? So if this is negative, you have to add 26 until it becomes positive, and then you say modulus 26. So Caesar used the key 3, of course. Yani now we can. So based on the key, this is the easiest cipher. So if k equals to 15 and we want to encrypt the word hello, h from here is 7. So we put number 7, and then E is 4. We put number 4, and then we add 15 to each one, which is what we did here. Okay? So 14 plus 15 is 29. Modulus 26, then it becomes 3. 3 is D, and so on. So this is the ciphertext. This ciphertext we send over the channel, and then we on the other side. On the other side, what we need to do is to convert this again into numbers, and then we subtract 15 from everyone. So again, 0 minus 15 is 11. Modulus 26 is 11. صح؟ فهمتها ليه دلوقتي؟
minus 15 plus 26 modulus 26.
Yes. Okay. So again, 3 minus 15 is minus 12. So we have to add 26. Okay, it becomes 14. 14 is O, and so on. So here we reach back to the word hello. Imagine. Okay. So that's very easy. So, is it easy? Okay, it's very, very easy. So So assuming that the attacker uses some kind of crypto analysis using ciphertext only, so I get this ciphertext. So using this ciphertext and knowing the fact that the encryption algorithm is just a simple Caesar algorithm, okay? So he can use the brute force technique. So assuming that k is equal to, I know that k has to be from 1 to 25. Because obviously this is not a readable text. Or otherwise it's a simple plain text and it's already readable. So I use k equal 1, I get this. I use k equal 2, I get this, until I get, at k equal 7, I get something that looks like it's not very secure. So it looks like it's readable in a way. So I would say, okay, so there is a very high probability that k in fact is equal to 7. So I use 7 for future plain ciphertext, and I see if it still looks readable. If that's the case, then I say for sure k is equal to 7, and then I can break the communication in that case. So this is using the crypto analysis using ciphertext only. And in that case, we use brute force techniques. The last thing is what we call multiplicative ciphers. Multiplicative ciphers, similar to additive ciphers, we take the plain text, we multiply it by the key. So again, it's based on substitution. This is substitution cipher. But we substitute a letter based on its value and multiplying that with the key, not adding the key in that case. Okay? So we get the plain text, we multiply it by k, and then we calculate the modulus based on 26. Okay? So the question is, can we, on the other side, divide? No. No. Division, modulus 26, is not the mirror of multiplication, modulus 26. That's the bad news. Okay? So instead of dividing by k, which is wrong in that case, we multiply by the inverse of k modulus 26. What's the inverse of k modulus 26? We teach that in master's level. You're not required to know how to get the multiplicative inverse of any number modulo 26 or modulo any number. ماشي كده؟ So if I give you an exercise like this, I have to give you the inverse of k, the multiplicative inverse of k. Okay? So the additive inverse of k is minus k. We know that. Okay? And if it's negative, we add 26, and we know how to do that. The multiplicative inverse of k, which is k to the power minus 1, is not simply the inverse. Imagine? For example, the multiplicative inverse of 7 is in fact 15. Okay? So you can look at the videos to know how to calculate this. It's not required. You're not required to know. And if I give you an exercise like this, I have to give you the multiplicative inverse of k. واضح كده? If I give you this, then the decryption is exactly like the encryption, but using the multiplicative inverse. But it's the exact same thing. Okay? So you multiply by k to the power minus 1, which in that case, instead of 7, you multiply by 15. Okay? Any question? عضل. تمام؟ كله تمام؟ Everything's clear? تمام.